Hi everyone, welcome to the final module for Kidneys 7103, where we'll be talking about models that have ill-mannered error terms. We'll expand on that and explain exactly what we mean by that over the course of the following lectures. But first, let's talk a little bit about the assumptions that we've had in our models so far. So remember that we've been using this general format of our data is equal to our model plus error, right? Which if we expand mathematically is the individual y's, right? The individual data points that make up our data can be explained by some linear model, which is a combination of various parameters that we're estimating, and then the variables that we choose to include in that model. And then the difference between what our model actually predicts and the actual data is what we would refer to as error, or the residuals that are left behind after we've tried to fit these predicted values to the real data. So in these models, we've made a few important assumptions about our residuals, or those epsilon terms. The first is that these are actual independent residuals, right? That there's no statistical relationship between the residuals, and they're coming from independent observations. Now, in chapter 11 of the textbook, we discussed how we can actually handle situations where we have crossed or nested designs that create statistical dependence in our error terms. And so this is probably the most important of our assumptions, is recognizing when we have dependence, right? When we have observations that are coming from related people or related sets of information in some way, and controlling for that statistical dependence in our data. If we violate that assumption, we can get a very wrong answer very quickly. So the independence assumption is probably the cardinal assumption that we never want to violate. However, we have some other very important assumptions about our data, which are that they're going to be, about our error terms, I should say, not our data. We have some other very important assumptions about our error terms, which are that they are normally distributed, which we refer to as the normality assumption, and that they have a constant variance, which is referred to as the homoscedasticity, or the homogeneity of variance assumption. So these two assumptions are still quite important. And the p-values that we calculate assume that these assumptions are totally correct. As we'll see, it's not always the case that these things are totally correct. And to some degree, you can violate these assumptions, right? But we want to be very cautious about these assumptions, because if we violate them to a large degree, that means our p-values are going to be wildly inaccurate, right? And we don't want wildly inaccurate p-values. We want reasonably accurate p-values. So we need to make sure that our normality assumption is reasonably satisfied, and that our homoscedasticity assumption is reasonably satisfied. And we'll be talking about methods for actually making those assessments as we go along. Outside of formal regression assumptions, though, we also have to be worried about other issues in the behavior of our data and how that shows up in our residuals. So here, for instance, we have four different relationships between x and y. So these are just arbitrary x values and y values plotted against each other. But in these four different panels, you can see that the data have very different distributions. Interestingly, though, if you were actually to fit a linear model to these data, what you would end up with is exactly the same intercept and exactly the same slope. And furthermore, you'd have exactly the same p-values, because the underlying standard errors for both of these things are the same as well. So if you were to just look at the fitted values and their statistical significance, you'd end up with exactly the same conclusions, because all these lines have exactly the same slope and intercept, and all these lines have exactly the same statistical significance in their slope and intercept. However, if we look at the raw data, we can see that that's not all we should interpret, right? We can see that only example number one really represents what we would think of as a fair linear relationship between x and y, whereas x increases, y is generally increasing. And yes, there is some variability in that relationship, and there's some error to it, but on average, that looks like a pretty reasonable linear relationship. In example number two, we can see that there's actually a pretty pronounced curvilinear relationship between x and y. So even though as x increases, y increases, the linear fit actually isn't very good. And if we had gone with a nonlinear or a curvilinear fit, we might have actually been able to explain each of these data points perfectly. Because although the linear fit is noisy, the curvilinear fit would have been almost perfect. Similarly, in example number three, we can see that we had an almost perfect relationship between x and y, were it not for one outlying value here that gives us an unusually high y value, given the other y values that we see in the data set. Now, it could be that that particular data point has an error in it. It could be that that data point comes from a slightly different population, right? But whatever it is, that one data point is the only thing that's keeping our model from having a very different, flatter slope that would perfectly explain all of the other data points. In figure 4, then, we see kind of a similar situation, but now we have something that's an outlier on both y and x, right? So for all of the other values, they all had the same x, but a lot of variability in y. So regardless of what x value there was some variation around y. For this one data point, though, which now has an extreme x value and an extreme y value, we actually then get a slope that matches the other situation, like we had up in panel number 1, even though the underlying data look very different. So in panel number 1, we think that that slope and intercept is a good description of the data. In panel number 4, that slope and intercept don't really seem to be a good description of the data, because our data otherwise look like a pretty straight line were it not for that one data point that is exerting undue influence and creating a slope and an intercept in our model. So these figures were developed by a statistician named Anscombe, and are referred to as Anscombe's quartet, in a paper published in 1973. And these figures highlight the importance of always graphing our data before we analyze it, because graphs are a great way to quickly and easily understand some of the distributional assumptions of our data. But it's also a helpful reminder that we need to check our regression diagnostics, and we need to check our regression assumptions. So diagnostics versus assumptions, these are related terms, but diagnostics are generally ways of looking for what the book refers to as idiosyncratic errors. We want to see, is there any data point that has an extreme X value and might be exerting leverage on the model? We want to see if there's any point that has an extreme Y value and might be an outlier in terms of its residuals, and it might be pulling the model in one direction or the other. We can also look at the conjunction of those two things to see if any one data point has undue influence on the model, and it's actually substantially affecting either the direction or the significance of a slope or an intercept that we're trying to estimate. Beyond those idiosyncratic errors, though, we can also check for our assumptions of our actual general linear model. And so when we check the assumptions, these are more systematic things. Rather than individual idiosyncratic features of data points, systematic errors are if we're violating the assumptions broadly across the residuals. So in kind of the first case, we're considering individual residuals. In the second case, we're considering all of our residuals collectively to see if our assumptions are satisfied. And we need to check the assumptions of normality. That is to say, do the residuals follow a relatively normal distribution? And we need to check the assumption of homoscedasticity, which is to say, do the residuals have a relatively constant variance across all the different levels of the model?